I'm 12 years old and in 7th grade. I was curious about cars and aerodynamics. So, after talking to my grandpa, who's an engineer, we decided to dig in and experiment with shape and wind. As we kept talking, I decided that the purpose of my science project would be to investigate how the shape of a vehicle affects how far it can travel down a ramp. So I decided to title my project Sailing Cars. The question that helped guide my research was, how does the size of a sail and wind affect the distance a car can travel down a ramp? Which leads me to my hypothesis, which is, when a car is sent down a ramp with a sail attached and a fan at the end of the ramp, the car with the smallest sail will travel the farthest due to air resistance and aerodynamics. How I did my testing was I set up a Hot Wheel ramp with a fan at the end, as seen in these photos. Next, I cut out 3 sizes of vellum. The sizes I made were 2" by 2", 4" by 2", and 3" by 4". Then I sent the Hot Wheel car down the ramp with the various size sails and with 3 fan speeds turned on. I sent the car sailing down 12 times per speed per sail. Each time the car stopped on the ramp, I measured the distance that the car traveled. I measured it using centimeters. For this experiment, the distance the car traveled was the dependent variable. The independent variables were the size of the sails and the fan speeds. The control elements were the slope of the ramp and the car. The first time the car sailed down the ramp, I didn't turn the fan on at all. The average distance traveled with the 2" by 2" sail and no fan speed was 566.3 centimeters. The average distance traveled for the 2" by 4" sail was 450.0 centimeters. Finally, the average distance traveled by the 3" by 4" sail was 406.8 centimeters. Next, I sent the 2" by 4" sail down with fan speed 1. The average distance traveled was 337.2 centimeters. With the next fan speed 2, the average traveled was 327.8 centimeters, and with the last speed, the average distance traveled was 287.8 centimeters. And I basically did the same thing with the 2" by 4" sail. With fan speed 1, the average was 231.4 centimeters. With fan speed 2, the average distance traveled was 220.6 centimeters, and speed 3 was 210.3 centimeters. And for the last car sailing series, the average distance traveled for the 3" by 4" with speed 1, the average was 196.0 centimeters. Speed 2 was 185.8 centimeters, and speed 3 was 162.3 centimeters. All of the results I just discussed can be seen on these graphs. After conducting this experiment, I have concluded that the shape of the car and wind resistance do affect how cars travel. My experiment showed that the car with the smallest surface area went the farthest distance. This happened because the car had less surface area fighting with the wind. So this means in everyday life, the shape of the cars we build affect the way that it travels on a road. So, if people want to go farther with less power, choosing an aerodynamic car is important. In my experiment, the 2" by 4" sail could be an example of how a small 4-door car could travel, and the 2" by 4" sail could represent a Suburban, which is bigger than a car and has a harder time moving through the air. And the 3" by 4" sail could represent how a huge semi-truck might move on a road. If I were to do this experiment again, I would choose a ramp that doesn't have connected segments because I wonder how it affected the way the car traveled down the ramp. In conclusion, I learned that aerodynamics are a really important part of our world because aerodynamics affect the way a car travels. Good aerodynamics will help a car move farther with less effort, and bad aerodynamics will help cars have to work harder to get the same amount of distance as a car with better aerodynamics. Thank you for listening to my presentation about sailing cars.